Welcome to today's webinar. Our topic today is stainless steel in construction. The webinar is organized by the New Zealand Stainless Steel Development Association, the University of Canterbury in Christchurch, the Steel Construction Institute, and it is conducted by the International Molybdenum Association and the Nickel Institute. Today's presenter is Ms. Nancy Badu, Associate Director to the Steel Construction Institute and Consultant to the Nickel Institute. Our panelists of today are Dr. Koh Tsiang, Lecturer in Structural Engineering, and Paul Geppert, Executive Director of the New Zealand Stainless Steel Development Association. I'm your host, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Nancy.
Let me start by just explaining I work for the Steel Construction Institute. We're member-based and we exist to promote the use of steel in construction, and my particular field are high-performance steels. But we work in a range of fields, from reuse, bridges, offshore structures, etc. This is the program for the next 4 weeks. It's just me, I'm afraid, today. And then I'm joined by colleagues, experts in the field of stainless steel and structures for the next 3 weeks. So I have tried to design the webinar program so there's something for everyone and lots of chance to ask questions. I've put my email at the end of this presentation, so if you have a question in the week and you think, oh, it'd be really useful if you covered this or that, please don't hesitate to get in touch. A lot of what I say today you can access free of charge in the design manual for structural stainless steel. It's written as a sort of amplified Eurocode handbook, and I know you may not be familiar with the use of Eurocodes, but a lot of the information we've got in this guide is generic, and I think you'll find it useful. And next week I'll be talking more about the American and the European design standards, and I'll bring to your attention more design tools and design information. Today then, roughly split into 5 parts. This is our menu. I will start off with an introduction. Perhaps you know some of this already, but let's just whiz through that. What are we talking about? Let's explain what stainless steel is. Well, it's a family of corrosion and heat resisting alloys of steel. There's a wide range of them. In fact, you're never far away from stainless steel, whether you're in the office or at home. Stainless steels, there's a range of strengths, of corrosion resistance, and of other interesting properties. But what all stainless steels have is at least 10.5% chromium content. And with that 10.5%, you can see from the diagram, you get a tightly adherent layer of chromium oxide, which clings to the surface of the steel and protects the steel from corroding if you've got moisture and oxygen. If you damage the surface of the steel by scratching or whatever, then the chromium oxide reforms instantaneously. And that's what makes stainless steel protected from corrosion. All these stainless steel alloys, they're grouped into 5 distinctive families that have different microstructures and mechanical, physical properties. Different corrosion resistances in various service environments. And the families have different alloying combinations. So we've just seen that great video on nickel. Well, nickel is useful because that improves the formability and the weldability of stainless steels. And you need the chromium and also molybdenum and nitrogen to increase the corrosion resistance. So let me quickly run through these 5 families. Austenitics, they're the most important for today. So they're very ductile, they're reasonably strong. Your kitchen sink will be made of austenitic stainless steel, readily welded, and they work hardened, so the strength increases as they're worked. Duplex, now this isn't a layer. Duplex is actually the microstructure. It's a mixture of austenite and ferrite. Now, these are stronger than austenitics, but not as easily formed. Then we have the family of ferritic stainless steels, and they generally are useful for thin gauge applications, where perhaps galvanized steel isn't corrosion resistant enough. Often they're used internally for shop fitting. And then the last 2 families, precipitation hardening, pH steels, they're very strong indeed. And they're used often for high duty rod, bar and fasteners for the aeronautical industry. And finally, martensitic stainless steels. They are also high strength, used in valves, knife blades and dies. The families used in construction are mainly the austenitic stainless steels. Duplex stainless steels are being used more and more now, and ferritics also find some applications. I've summarized in this slide. So the austenitics, the family gives a wide range of corrosion resistant. Interestingly, they're not magnetic, the austenitic stainless steels, which you wouldn't necessarily expect. And the duplexes, well, you'd think about using a duplex if you've got an application where you can exploit the higher strength. So not if your design is going to be limited by serviceability, deflection, for instance, but if it's going to be limited by strength, then you'd be good to think about a duplex stainless steel. And as you would expect, the higher the alloy content, the more corrosion resistant and the higher the cost. On this slide, I am suggesting the reasons for using stainless steel in structures. And clearly the most common reason is if your structure is in a highly corrosive environment, or where it's important to have a long life with low maintenance requirements. Perhaps you've got an application where you really don't want a painted coating for corrosion protection, or a certain attractive aesthetic appearance is needed. Those are all reasons for using stainless steel in structures. The less widely known reasons include if you need a non-magnetic steel, as I've mentioned, in some medical and defense applications, that's important. Also, if you need good toughness at very low temperatures, then the austenitic stainless steels are a wonderful choice. And finally, I'll show you in a few slides' time that the stainless steels offer very good impact properties for high strain rate events. We're going to go around the world now. I'm going to show you some applications. My main motivation is to show you the diverse range of applications you can find for load-bearing stainless steel components, large or small, hidden or on view to everyone. Let's start with buildings and external structures. Perhaps you'll recognise the gap in Western Australia. That's a duplex stainless steel walkway. No need to wonder why stainless steel was needed there. Very exposed, salty environment. But this photo beneath that, you may be wondering why stainless steel would be needed. And that is because the columns for the canopy in front of the building need to have a very high impact resistance to prevent the possibility of damage by vehicle impact. So that's a duplex stainless steel structure. And the rather beautiful canopy on the right, that's stainless steel, I think, was chosen because it was a very fixed and beautiful surface finish, reflective finish needed. Stainless steel and glass structures seem to be a popular choice over the last 10 years for entrances to subway stations or the like. And a couple of photos here from London where stainless steel has been selected. And also whizzing over to the States. Here we've got 42 canopies for the Washington DC Metro, all using austenitic stainless steel. I like this because every canopy is slightly different depending on the requirements of the given station. And a modular design has been adopted. So the modules are bolted together on site and they're delivered in as large as possible modules as can be delivered. So they're rectangular hollow sections, and I think rather beautiful designs. I think they've commissioned more than 42 now, actually. Clearly, stainless steel is used for cladding high-rise buildings in very demanding applications. Here in Dubai, the environmental conditions can be quite extreme: strong winds, sandstorm, high salinity, and stainless steel performs very well here. And there are many sculptural applications of stainless steel too. But perhaps what you're most interested in today, I'm not sure, is industrial applications of stainless steel structures. So we don't see these every day, but the largest proportion of stainless steel goes into these types of applications. Now, I mustn't spend too long talking through these, but the photo on the top right, that's a biopharmaceutical production plant where all the sections are 304 stainless steel welded together. And you'd think, well, why do you need stainless steel? Well, because these clean factories, you need to carry out maintenance and inspection of the vessels, and there can't be a chance of any painted coating falling off. All the surfaces have to be very readily cleaned. Then we have, I've shown you an industrial skid for machinery in the middle top, and then the top right is a desalination plant in London. And then along the bottom, walkways and platforms, lock and dam gates. And the bottom right is actually a nuclear plant, an AP1000 reactor, where you have this sandwich construction, stainless steel, concrete, stainless steel. And that has been used quite a lot in plants in China and the States. What about the water industry? Well, just in November last year, we published an update to the information and guidance note on applications for stainless steel in the water industry. And although it's written for well, mainly for the UK market. I think there's lots of really useful information about what stainless steels to use in what different environments that you would encounter in the water industry, and written by top experts in corrosion. Not me, I should hasten to add. I'm just a structural engineer. But if you are involved in the water industry, I suggest you download this publication, because lots of useful applications for stainless steel there. Oh, I just work with someone who was involved in rather impressive stainless steel tower there, pretty tall, 9 meters tall, 3.5 meters square, a duplex stainless steel. Bridges. I'm going to talk at the end of this webinar more about bridges, and perhaps it's surprising to you to consider using stainless steel for such a large structure. But depending where your bridge is, it can actually save you lots of money using stainless steel and not having to do regular painted maintenance. More on that later. But there are examples of pedestrian bridges made of stainless steel, railway bridges, and also road bridges made of stainless steel. And of course, I should show you your fairly new bridge in Sydney, Australia, which uses stainless steel in a few different ways. You can see there's plate used for the primary deck structure, and then the compression struts are also made of duplex stainless steel, and then a high nickel alloy for the pins with austenitic stainless steel for the balustrades. So that's quite a nice example of different stainless steel alloys. But just in case you're worrying, thinking, well, those bridges come along once in a lifetime, I'm not interested. Just for regular bridges, stainless steel is being used. This is a road bridge in, well, I don't know, somewhere in Sweden, but not in a capital city. And lean duplex is being used just for a standard composite road bridge. And finally, on the applications, let me show you a wide range of fixings are used, because stainless steel is an important material for joining concrete, masonry, timber, aluminium, useful in renovation, repair, refurbishment, and reinforcement, all beginning with RE, fortunately. I think you'll have come across quite a few of these stainless steel products. Moving on to stainless steel properties now. Here are the stress strain characteristics at the low strain. In red, carbon steel, clearly, sharply defined yield point, and then a plastic plateau. In green, I'm showing austenitic stainless steel, and in blue, duplex stainless steel. So you can see rather different stress strain characteristics. They exhibit strain hardening, which is when the strength increases with the plastic deformation. And it's gradual yielding, isn't it? A gradual loss in stiffness. And this behavior leads to differences in the performance of stainless steel beams, for example. The stiffness, modulus of elasticity, is very similar, carbon steel, stainless steel. And what we use in design, because there isn't a clear yield point, we use the 0.2%, the strength at the 0.2% strain. And this is a conventional metric used for any metals that have non-linear stress strain characteristics like this. It's not something special for stainless steel. Other metals like aluminium you would use the strength at the 0.2% proof strain. So that's what's tabulated in your product standards. These curves are the full range stress strain curves. And of stainless steel and carbon steel, and you can see that austenitic stainless steel is much more ductile than carbon steel, and it also shows greater toughness, which is compared to the area under the stress strain curve. So stainless steels, they have better energy absorption properties than, for example, aluminium. They have a high rate of strain hardening and, as I said, excellent ductility. And I show this photo with this slide because the point is that the damage to the stainless steel rail cars was contained within a very localized area because of the good energy absorption properties. So we'll think a little more in this webinar, but a lot more in the webinar next week about the impact of these stress strain characteristics on our work as structural engineers. How do the design rules differ? And actually, can we use these characteristics to get more out of the stainless steel? Because it's more expensive, so we want to use it in the most efficient way possible. On this slide, I've summarized the mechanical properties. So for carbon steel, I'm comparing against an S355 carbon steel. Austenitic stainless steels, you'll see they have a lower yield strength, 0.2% proof strength, and the duplexes have a somewhat higher yield strength. The tensile to yield strength ratio, well, for carbon steel and duplex stainless steels, it's pretty similar. For the austenitics, it's much higher, around 2.4. This is because of the strong work hardening. The elongation, again, carbon steel, duplex, similar, and the austenitics have about twice as much elongation. These properties are in the annealed condition. You'll hear this strange word a lot with stainless steel, but it's used to describe the properties in the softened, or sort of, they will never be lower than the annealed condition, and they'll more or less always be higher. If you buy some stainless steel plate, for example, it will be extremely surprising if the yield strength is as low as 220. Let's think about physical properties now. And here I've compared the thermal expansion and the thermal conductivity. The density is more or less the same, as you can see. Expansion then. The austenitics have about a 30% higher expansion than carbon steel. So when you use carbon steel with austenitic stainless steel, you should take into account the differential thermal expansion in design. Conductivity, well, that's different again. Austenitic and duplex stainless steel, the conductivity is only about 30% that of carbon steel. This is good and this is bad. Materials with low thermal conductivity, they prevent the transfer of heat. So this helps in achieving enhanced energy efficiency. For example, lower thermal conductivity makes stainless steel ideal for developing, say, thermal brakes. But it's also a disadvantage, say, in welding, where you may get more distortion because the heat isn't conducted away as quickly or efficiently. Now let's finish off the properties section with this slide on low temperature toughness. I think what you'll notice is austenitic stainless steels, they actually show no ductile to brittle transition. Isn't that interesting? So you can use, and indeed they are used, right down to cryogenic temperatures, for example, for LNG containers. Duplex stainless steels, just like carbon steels, they have a ductile to brittle transition. It's similar-ish to carbon steels. There's been a lot of work on this recently because it's an important parameter to fully understand, and there is complete and comprehensive guidance now in the forthcoming Eurocode for duplex stainless steels on low temperature toughness. Good. Now we're going to move to specification. And I want to try and explain the way stainless steels are named. This might look horrifying to you, but depending what product standards you're using, the same alloy will be called, will have a different designation system. In Europe, for example, we use this number like 1.4301. Also, the European standards give this very complicated name for each alloy, but no one I know has ever used that, so you can forget that. Now, in your part of the world, you would be using the American ASTM designation system, because I checked that in the Australian New Zealand standard 4673, which covers the design of cold form stainless steel structures, I checked how you designated your alloys, and for the austenitic alloys, this standard covers 304, 304L, 316, 316L. So these are there in red. For the duplex alloy that is covered in your standard, it actually uses the UNS, Unified Numbering System, which has the S at the beginning, I think, because it's steel or stainless steel. I can't remember. Steel, I think. And why your standard uses that is that there isn't an ASTM official number for this particular alloy. It's a commonly used trade name, so it makes sense that they decided to use the UNS. And then your standard also covers the ferritic stainless steels, 2 alloys, 409, using the ASTM system, and it covers another ferritic alloy for which there isn't an ASTM. And so actually, I'm not quite sure why, but it was decided to use the European number for that one. But anyway, hope that's all obvious to you. For this presentation and the rest of our presentations, we will be using the ASTM system. When we use the term stainless steel grade or type, we mean an alloy, a chemical composition. We're not talking about strength. Now, this is confusing if you're familiar with the American standards, because they talk about steel grade 50, and 50 is the strength, isn't it? It's 50 KSI yield strength. But that's not the case for stainless steel. When we use grade or type or alloy, we mean the chemical composition. And I try to use the term alloy, but forgive me if I drop back into grade. The other thing I wanted to explain is what this L is up to, because you've already seen 304 and 304L. So L stands for low carbon. And low carbon grades used to have to be specified if you were going to carry out welding, because having a low carbon minimized the risk of a certain type of corrosion happening, sensitization. Now, these days, more or less all stainless steels that are made actually end up low carbon. And so you see something called dual certification. You'll see the alloy written as 304, 304L, and that provides the material with the higher strength. 304 has a very slightly higher strength than 304L, and it has the lower carbon content of 304L. So what I mean is it's the best of both worlds. So don't be surprised if you see austenitic stainless steel dual certified like that. So now we get to the issue of how do you know which of these alloys to use for your application? And right, I need to speed up, don't I? I've taken this from our recent guide for the American Institute of Steel Construction, and I just want, although it looks complicated, the steps are quite easy. The first thing you have to do is understand the environment. If it's atmospheric, what's the chloride salt deposition? Is it close to the sea? Are there de-icing salts? Are there other nasty pollutants? Is it washed by the rain? Or is it sheltered? Will it be cleaned? If your application is immersed, what are the chemicals? What's the composition of the liquids? If your application is in an industrial process, are there sulfides? What are the other chemicals, etc.? Once you've characterized the environment, then you need to think of your design requirements. What surface finish do you want? Will there be lots of crevices? What are the design details? From that, you can move on to select your candidate alloy. And then, of course, you have to think, well, is this product actually available? And what's the lead time? So this is the sort of decisions that have to be thought through before you actually get onto the structural engineering, before you decide, right, I've got a duplex. This is my 0.2% proof strength. Let me get on with determining the buckling of this member. Now, there's lots of guidance about how to select the right alloy for application, and I've put a couple of ideas here. We'll talk more about the AISC standard next week. There's a very useful system on the IMOA website, International Molybdenum Association website. Lots of very helpful guidance there too. Let me whiz through these just to highlight the fact that the 304 alloys, they're the standard chromium nickel alloys. The 316 alloys, they have molybdenum, which makes them more corrosion resistant and more suitable for applications, for example, by the sea. Austenitics are widely available in a range of product forms. The duplexes, we have the lean duplexes, which have lower alloy additions. That's why it's lean. And then we have the standard duplex. Standard duplex has been around for years and years and years in the chemicals industry, available in a wide range of product forms. The lean duplexes, well, in the last 10 years, a range of lean duplexes have been found to be tremendously helpful, and they're increasingly used. A few thoughts on finish. Clearly, mill finishes, you have a 1D or a 1 finish on thicker products. If you've got thinner material, then it would generally be a cold rolled finish. These are all specified in the product standard. You can have special finishes, whether ground, right up to bright polished, patterned, coloured. The important thing is that you shouldn't just specify, I don't know, I want a 240 grit, because that depends on the belt, the pressure, the speed of operation. It is better to specify the RA value and be more precise about it. And I hardly need to say, but the finish has a significant impact on the corrosion resistance. Why? A rough finish is more likely to retain contaminants than a smooth finish. Rain washing is less effective on a rough finish, and a rough surface will have these micro crevices. So you can see the photo on the left, both put out by the sea for a year and a half. The mirror polish looks great. The mill finish, the 2B, is showing a few signs of pitting. A range of structural products is available in stainless steel. And so you need to pick the right product standard. So in the world of ASTMs, you need 2 standards to specify most products. One covers mechanical properties and chemistry, and one condition finish tolerances. So these are the ASTMs for flat material. Then you have different ASTMs for bar and shapes. And then another different ASTM for your hollow sections. What about fasteners? Well, here they are specified to an ISO 3506. Part 1 covers bolts and Part 2 nuts. Let me just explain the numbering system, because it's sort of annoying, but it doesn't use the same designation system as the flat material. First of all, you start off with a letter A for austenitic. Then you have a number which defines the corrosion resistance. So A2 is equivalent to a 304, or A4 moves you up to a 316. And then the final number, be it 70, 80, that defines the property class, so that's the strength. So property class 80 means that the tensile strength is 800 megapascals. So very similar to a grade 8.8 bolt. And property class 70 and 80, they're very widely available. Property class 100 is newer, so that's not as widely available. But typically you'd use an A270 or an A470 or 80. Exactly the same system for duplexes, D for duplex, D2 and D4, these are the sort of lean duplex grades. This is all explained in ISO 3506, and D6 is the standard duplex. I finished specification, and now for the remaining 5 or 10 minutes, I wanted to tell you about a project that we carried out at SCI over the last, well, it actually took us ages, took us 2 or 3 years. This was the purpose of the project, to compare the construction and life cycle cost of a duplex stainless steel highway bridge, and to compare it against an equivalent carbon steel bridge. And we worked with teams from Arup, from the materials, bridges and transportation, infrastructure, asset management departments, and we worked with some stainless steel producers, fabricators, and the UK Steel Bridge Group. This was our bridge, a typical highway bridge in Europe, 2-span integral bridge, 2-lane rural roadway, 4-girder arrangement. As you can see, the reinforced concrete deck acts compositely with the 4 main girders. And the main girders were divided into 5 portions so that their cross sections could be optimized to resist the loading, and they were connected by pretension bolts. So we looked at carbon steel painted, weathering steel, and duplex stainless steel. We did the design to the Eurocode. So I'm showing here some of the connections and the bracing and stiffeners. So firstly, on this slide, I'm showing the tonnage of the steel girders. As you know, for weathering steel, you have to have a corrosion allowance. So that's why the weathering steel plate girders were heavier. I've just shown S355. If I had also fitted on S460, then there's about a 15% reduction in weight. So the S460 bridge weighed about 56 tons as opposed to 66 for the S355. So that was the easy part, designing the bridge. Then it got a bit more challenging because we defined a fabrication specification for the three materials of bridge. We again use the European fabrication specification and then what the Highways Agency requires in the UK for bridge structures. Then we went out to tender to get realistic fabrication costs, and this got a bit tricky because we found it was impossible getting direct comparisons. We were comparing apples with pears as opposed to apples with apples because we really needed quotes from one fabricator who worked in the same country, who used all the same assumptions. And this proved to be rather difficult because stainless steel bridges is a fairly new market, and a lot of carbon steel bridge fabricators haven't yet used stainless steel. So in the end, we decided to make an intelligent assumption about the cost of fabricating the duplex bridge. Rather conservative. We did upper bound, lower bound, guessing it might be between 30 and 70% more expensive than fabricating an equivalent carbon steel bridge. Why? Well, a few reasons. You need a dedicated fabrication area, higher standards of cleanliness. Welding is a bit trickier with duplex because you have more movement, more spring back, and you have to tightly control the temperature during welding. So there'd be extra costs for preventing distortion or correcting them. You have to use non-carbon steel tooling. So we just felt that if we used an upper bound and lower bound, I think for all the calcs, we ended up using the upper bound, but then we did a sensitivity study at the end. And we assumed that the erection cost would be 20% more for stainless steel. That's probably very, very conservative. So let's move on. Just looking at construction costs to start with. Here we have the costs for the carbon steel bridge, around 300,000. Very similar for the weathering steel bridges, and the stainless steel bridges significantly more expensive, which was no surprise to us because we know that stainless steel is more expensive than carbon steel if you're comparing ton by ton. These pie charts show the total construction costs of the bridge because clearly it's not just steelwork, there are foundations, there's the slab, all manner of other items. So you can see that for the carbon steel options, which are the top two charts, the cost of the steelwork was about a quarter of the total construction costs. And for the stainless steel bridges, which are the lower two, the material costs were higher, 37% to 42%, something like that. So what can we conclude if we're just looking at construction costs? The lean duplex was about 80% more costly than the painted carbon steel, and the standard duplex was more than double. If we consider the steelwork only, if we think of the total bridge, then the lean duplex was about 20% more, and the standard duplex was about 31% more. Life cycle costing. This is where you consider both the cost at construction and also operation and maintenance throughout the life of the bridge. So to define maintenance, we had to come up with some locations. So we chose 4 locations: a bridge over a main road, bridge over a railway, a bridge over a railway near the coast, and a bridge over an estuary. And each of these had different levels of maintenance difficulty. So this is where we worked with the Arup Asset Management Department, because this was well outside our expertise, and we used the software tools that they use in order to plan the life cycle costing for their structures. So this was based on a very complicated spreadsheet originally from the London Bridge Engineering Group. It modelled deterioration of different components and maintenance works, etc., etc. By the way, this is all detailed in a freely available report. If anyone's interested, I can send it to you. We assumed a service life of 120 years. This is what might well be assumed in the UK. I'm not sure what it is in New Zealand. We assumed the bridge carried a local load with a low annual average daily traffic, nominal maintenance every 10 years for principal inspection and miscellaneous repairs. And we assumed the duplex stainless steel and the weathering steel, well, they clearly didn't require any repainting, so they didn't require maintenance for 120 years. We did not include indirect costs of maintenance. Now, these are very varied. They're difficult to define, and they can be enormous. For example, traffic congestion delays, environmental damage, business effects. They typically have to be inferred and monetized. For example, observation of increased fuel consumption. And so it just wasn't possible to include them in the study. But research by others shows that these indirect costs of maintenance can significantly exceed the direct cost of maintenance, depending on the particular site. Did we consider real or present discounted costs? In any life cycle cost study, clearly you have to consider both types of cost. And we discussed with clients which was most useful, and they said we're interested in both the real, assuming the cost incurred at the start of the bridge's life, and the discounted. So, nearly at the end now, let me just talk you through 2 more slides. So this was the outcome of the life cycle cost study for the steelwork only. The next slide is for the total bridge costs. Blue, that's the construction cost, and the green is the maintenance. So location 1 is here, and for location 1 and location 2, we included weathering steel, but for the location by the coast and the estuary, weathering steel wasn't suitable. So that's why we've only got 2 options. So location A and B was lean duplex, and location 3 and 4 was standard duplex. So the conclusions would be that the cost of repainting is at least as significant as the construction cost of carbon steel. Well, that's interesting. For bridge over rail, the cost of repainting the carbon steel was actually twice the construction cost. Very expensive, as you know, it's obvious, isn't it? You have to shut the railway. For bridge over the rail, the duplex stainless steel was cheaper than the carbon steel, irrespective of how corrosive the environment was. And when weathering steel is viable, locations 1 and 2, yep, it's the cheapest. You can see that. So these graphs are steelwork only. Let's look finally at the total bridge costs for 120 years. And please note different vertical scales. For location 1 and 2, we go up to 10 million, For location 3 and 4, we're going up to 25 million. So that's important to note. So again, looking only at the present costs, which are always the second bar for each option, maintenance cost is still as significant as the construction cost, except for location 2. As the corrosiveness of the environment increases, for example, as we go from location 2 to location 3, the repainting cost increases. That's obvious, but its significance relative to all the other total maintenance reduces. That's because everything's really falling apart by the end of 120 years. For the bridge over the rail, again, duplex was cheaper than carbon steel. So that's important to note. And again, weathering steel, when it's viable, it was the cheaper option. So just wrapping up the conclusions from that study, carbon steel, the repainting, always looking at the present costs, the repainting present cost was greater than construction cost. And it was the bridge over the railways where you got the most benefit from using duplex stainless steel. A reminder that we made a number of conservative assumptions. We assumed fabrication was 70% more, erection 20% more. We didn't consider any of the indirect costs arising from maintenance. And my conclusions, let me just whiz back, my conclusions have all been geared around the present costs. So the arguments in favour of stainless steel are much clearer. If you look at the real costs, clearly you can see these very tall bars. Our time's up. I hope I haven't talked too fast. Let me conclude. Stainless steel is a corrosion-resistant family of steel alloys used in construction in aggressive environments where maintenance is difficult, and often for architectural reasons also. It's important that the right alloy is chosen for the particular environment. You don't want to overspecify or underspecify. Construction costs may be higher, but for certain applications with long design lives, such as bridges, life cycle costing will demonstrate that stainless steel can save you money as well as enhance safety. And there are many resources available to help you. I'll run through them in more detail next week. Thank you for listening, and see you next week.
Thank you very much, Nancy. Dear listeners, if you have any questions concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you fastest. Thank you all for attending this webinar, and we are looking forward to have you on one of our next webinars again. Thank you and goodbye.